Hello everyone. So today we will learn about the crystal field theory. So crystal field theory explains the complex formation between the metal and ligand on the basis of electrostatic attraction. Electrostatic interaction between metal and ligand. There are different metals which form the complexes such as cobalt, manganese, etc. And there are various ligands which binds with this metal to form the metal complexes. Ligands such as Cl-, F-, NH3, H2O. So now you must have been wondering that I mentioned here that CFT explains complex formation on the basis of electrostatic interactions, but here the ligands are neutral. So in our electrostatic interactions, there are two types of interactions taken into the account by the crystal field theory. When our metal is charged, so it is in an ionic form, and when our ligand is also charged, it is also ion. So in this case there is ion interaction. Whereas when our metal is charged and our ligand is neutral, like in case of ammonia and water, so this one is our ion and this neutral ligand is considered as dipole. So in this case it is the ion dipole type of electrostatic interactions. Ion dipole interactions. So these are the two types of interactions taken into the account when we consider the crystal field theory for complex formations. So let's move forward towards let's see how complex actually forms by this theory. So our metal is considered as a point charge. Our metal is considered as a stationary point charge. Metal is considered as a stationary point charge, which is positive charge, and our ligand is considered as moving charge. It can be negative charge or it can be dipole. In case of neutral ligand, and negative charge in case of ionic ligand. This will just explain. I have explained this to you in the previous slide. So let's see how the octahedral complex forms by the crystal field theory. Before moving towards the octahedral complex formation and tetrahedral complex formation, I will explain how crystal field theory works and how it explains the complex formation. So first of all, our metal is considered as a isolated metal ion. This is our isolated metal. And this metal is in the influence of the ligand. In the influence of ligand. So this is the isolated metal and this one is the metal in the influence of ligand. Now in this case So we can see these two different cases. So in this case, our ligand is very far away from the metal. So when ligand is approaching our metal, so metal experiences two types of forces. Attraction forces between the, so there are two types of, so this ligand is approaching the metal. The arrow should be in this direction. So this ligand is approaching the metal from far away. So this metal is experiences two types of forces. Attractive forces and repulsive forces. So attractive forces are positive negative interaction, positive charge and negative charge, and repulsive forces are between the valence shell electron of metal and negative charge density of ligand. So this is the repulsive type of forces, which is between the valence shell electron of metal and negative charge density of ligand. So which one is our valence shell in case of metal? Our valence shell is d orbital. So now we will move forward towards seeing towards the how these repulsive forces direct our octahedral formation and tetrahedral complex formation. So I hope this is clear now, and let's move forward towards how there are different types of d orbitals and how they are arranged in the 3D space, so that we can get the idea of the crystal field splitting caused due to the approaching ligand. I will get back to this point, that isolated metal and the metal influenced by the ligand field. Before moving to that, I will explain the different d orbitals and their orientation in the 3D space. So there are 5 types of d orbitals. dx square minus y square, dz square, dxy, dyz and dzx. So now we will see one by one how these orbitals are arranged into the 3D space. So dx square minus y square, if we let this x axis, this one is y axis and this one is our z axis, then dx square minus y square is arranged along the axis. These are the lobes of these orbitals. You must have studied this in your previous classes of chemical bonding, but let's revise that for the sake of convenience. So this one is our dx square minus y square, which is arranged along the x axis and y axis. Now we will see dz square. dz square is an axial orbital arranged along the z axis. This is our dz square. Moving forward, these are our axial orbitals. And these three are our non-axial orbitals. So non-axial orbitals, as the name suggests, they are arranged in between the axes. So can you guess this one or this orbital? Yes, this is the dxy orbital. As the name suggests, xy, it is between the x-axis and y-axis. Similarly, if we let this one our z axis and this one our x axis, then this orbital is our dxz. And similarly, if we consider this our y axis and this is our z axis, then this is our dyz. So I think it is now clear that how these orbitals are arranged. So you can see there are axial orbitals and these three are our non-axial orbitals. These are our non-axial orbitals. So now we will move forward to see how our ligand approaches the metal ion and how our octahedral complex formation takes place. After that I will explain the tetrahedral complex formation. So let's move forward. So let's come back to our point which I explained earlier also. Let's suppose this is our metal ion and this is our isolated metal ion which is not influenced by any ligand and which is not approached by any ligand. So it is as it is. Now let's consider the same metal ion in the influence of ligand. Our this ligand is approaching this metal ion from the far away. Let's call this influenced metal ion. So during this approaching of the ligand, our metal ion experiences two types of forces: attractive forces and repulsive forces. Attractive forces are between positive charge of metal and negative charge of ligand, whereas repulsive forces are between d orbital electrons, which is our valence electrons, and our negative charge density of ligand. So there are attractive forces as well as repulsive forces between the metal ion and the ligand. Attractive forces are between the positive and negative charge of the metal and ligand, whereas the repulsive forces are between the electrons, the valence shell electrons of the metal and the negative charge density of the ligand. So now we will see how these forces, how these interactions will decide the fate of our complex, and based on these interactions we can define, we can get the exact shape of the our complex, like it will be a octahedral complex or it will be a tetrahedral complex. Now let's see that. Now this ligand is approaching our metal ion. In this case, let's consider our ligand is far away from the metal ion. So in this case there forms the crystal field around the metal ion. So this crystal field is when ligand is far away. This crystal field is uniform in nature. So now this crystal field is uniform in nature, in uniform direction of the metal ion. So in this case, the energy of the d orbital increases, but does not split as of now. The splitting of d orbital occurs when our ligand approaches. Our ligands are coming very close to the metal ion. So for the reference, I will say that this is our isolated metal ion. In this case, our d orbitals are in ground state. This is our ground state. Ground state d orbitals. And in this case, whenever ligands are far away from the metal atom, it experiences the uniform crystal field. So our d orbitals come to the excited state, but not yet splitted. This is our excited state. When moving forward, our ligand is approaching our metal ion and it will come close to the metal ion. So let's suppose our ligand is this. And ligands, when complex formation happens in octahedral complex, there are 6 ligands. So 6 ligands are approaching our metal from the 6 different sides. And in the octahedral complex formation, so now let's suppose our ligands are approaching very close to the metal ion. So ligands are approaching axially. Now we will draw the axis along which ligands are approaching our metal ion. So this each axis have, let me rub this. Each axis have one ligand. So these are the 1, 2, 3, 4, 5, 6. Sorry, these are the 6 ligands in octahedral complex. There are 6 ligands approaching from 6 different axes towards the metal. So now our metal contains 5 d orbitals: dx square minus y square, dz square, dxy, dyz, and dzx. So which are our axial orbitals? We have seen this just now. These are our axial orbitals and these are our non-axial orbitals. So when ligands are this close, let me give negative charges to this ligand so it becomes easy to understand. So when ligands are this close, it will affect the electron density of the metal atom, which are present in the axial orbitals. So this is our lobes of dx square minus y square, and this one is our dz square. So our dx square minus y square and dz square will experience the more repulsion by the approaching ligand, and our axial or non-axial orbitals, which are dxy and dyz, will experience very less repulsion. So as a result of this, we know as repulsion increases, our energy increases. We know this basic rule. As repulsion increases, our energy increases. So what do you think? Which orbital's energy will increase and which orbital's energy will be decreased? So yes, our energy of dx square minus y square and dz square will increase, and our energy, as these 3 orbitals experience less repulsions, its energy decreases. So our d orbitals are split into the 2 different energy levels called as T2g and Eg. G is a G rate which is related to the symmetries of these orbitals. So this is our d x square minus y square and dz square, which are our axial orbitals which energy level is increased due to the approaching ligand, and these are our dxy, dyz and dzx. So now our d orbitals are split into the two different energy levels. The energy difference between two energy levels is named as delta O, whereas O specifies to the octahedral crystal field splitting energy. Octahedral crystal field splitting energy, which specifies that our d orbital is split into the two different energy levels named as T2g and Eg. The energy of this excited state is marked as a barycenter. I will explain the concept of the barycenter to you. Like when our ligand is far away, we assume that there is a crystal field which is uniformly spread, and when our ligand approaches closely to our metal ion, that crystal field splitted into the two different energy levels. But as the energy conservation of energy principle says that energy must be constant. So this energy is splitted. This energy is only splitted into the two different energies. So if we consider this energy as 0, barycenter, then our sum of these two energies must be 0. So before coming to that, the energy from these to these is 3 by 5 delta naught, and this energy is 2 by 5 delta naught. This is 3/5 part of our delta naught, and this is 2/5 part of our complete delta naught. And when you take the weighted average of these two, it will contain the 0. Let me show this to you. As energy increases, this is if we consider the energy of barycenter as 0, then this one is plus 3 by 5 delta naught into 3, that is 3 orbitals, plus this is our negative energy, and this is considered as a minus 2 by 5 delta naught into 2. This comes as 0. Sorry. I made a mistake here. This must be 2, because in Eg we have 2 orbitals, and in T2g we have 3 orbitals. Then this must be 3, and it will come 0, which is our barycenter energy. So I hope now this is clear that the formation of the octahedral complexes, how the octahedral metal complexes are formed, is explained by CFT in this way. So now we will move forward towards the formation of tetrahedral complexes. To explain this tetrahedral complex formation concept easily, I will explain you octahedral complex in different manner. with the help of the cube. So each our face center will represent the ligand. So this is 6 ligands, and this is our octahedral complexes. Similarly, we can explain tetrahedral complex with the help of cube. In this case, our metal is on the center of the cube. I hope you can. Wait, just let me explain this. So, in this case, there are two types of So these are the two ligands. In the tetrahedral, there are 4 ligands, and these are the two ligands. Or this corner is in the back side, whereas our this corner is in the front side. Whereas our another two ligands will come from one from this corner and one from this corner. In this case, there are 6 ligands come from the faces of the center, and there are 4 ligands come from the alternate corners of our cube. So, if we draw the axis here, this is our x-axis, this is our y-axis, and this one is our z-axis. I hope this is clear. This is our z-axis passing through the back and front face. So if we draw the same axis here, our axis will pass through this like this is our x-axis, this is our y-axis, which is intersecting the sphere. This is our y-axis, and this one is our z-axis. I am not drawing the z-axis for the sake of simplicity. So you can now see that our ligand is approaching from in between the x and y-axis. Our ligand is approaching from between the x and y-axis. So now our non-axial d orbital will experience the more repulsion, and our non-axial d orbitals, that is dxy, dyz and dxz will be higher in energy when orbitals are splitted, and our axial orbitals, which are dx square minus y square and dz square, will remain lower in energy as this experience the less repulsion from the incoming ligand. Now we will see the splitting energy in tetrahedral, the splitting of metal in tetrahedral complex. So now this is our metal when it is in ground state. This is our d orbitals when it is in excited state. xy, dyz and dzx. Now in tetrahedral splitting, our axial orbitals will be lower in energy, whereas our non-axial orbitals will be higher in energy. And these headaches. This splitting energy is called as delta T. Whereas now this is our 2 by 5 delta T, and this energy is our 3 by 5 delta T. And the another important concept here is that our delta T will be always less than our delta O. This is our very center. But delta T will be always lower than delta O. Why? Because in our octahedral complexes there are 6 ligands approaching, which will possess higher repulsion. Repulsion very high. So this will cause orbitals to split more, whereas in our tetrahedral complexes there are only 4 ligands approaching. So our repulsion is less. There is repulsion but not as high as octahedral complexes. Therefore our splitting is less than delta O. Specifically, our delta O, our delta T will be equal to 4 by 9 of delta O. This relation you have to remember, and you have to remember delta T will always be less than delta O. So this is all about the crystal field theory and how our octahedral and tetrahedral complexes form are explained with the help of the crystal field theory. I hope this is clear to all of you. Thank you so much for your time and attention. Thank you so much. Take care.